Hi, I'm Matt Goska. I'm an engineer with Siemens in the U.S. working on CNC machines. This is part 2 of 2 in a series. If you haven't seen part 1, go down to the link below and watch that, because that's all the introduction for this video. Also down below is a link to a set of files, which is what I'm staring at here. I've already unzipped it. Go get that and follow along so you have your own copy. It's also very possible that what you download from that link may be slightly different than what I'm using, because that means I've updated it for some reason, either as an improvement or a bug fix. So what you'll get is, instead of this being a Word doc, you're going to get a PDF. And this is the instructions. If you're not watching this video, you can go through that on your own as well. This program, main minimum, is the main program that we're going to call to run my variant of Cycle 997. Or my replacement for Cycle 997. And what this main and main minimum, the difference is that main minimum is the bare minimum stuff that really needs to be in your program. Main is the program that I used when I created the video on the machine. So one of them is a stripped down example for your post development. The other one is, this is how it was used in the real world. So we'll go ahead and open this up and start staring at it. All right, so we've got some header stuff here. The first thing we have to do is you need to define some variables in your header. You can have comments before these, but no actual code, because they're variables, and that's just the way that syntax works. So the couple ones of these at the bottom, the target BCS and ball number values, these can all just be a dumb blind copy and paste into your post. The approach distance and ball diameter, this can all be intrametric, doesn't matter. You can either give them the ball diameter here, so what is the ball, size of the balls that you're trying to measure, and how far are you going to be standing off them. You can either enter those numbers up in the header here like I have, or you could put them in later in the program. It doesn't matter, whatever works better for your post. For that matter, if for some reason with your post, if it really is a hassle to enter these as variables and you'd rather just hard code the numbers wherever approach distance and ball diameter are called out, go ahead and do that. So there is some flexibility here. So this stuff is all absolutely required, or replacement and substitution. Anytime you see braces here like this is me calling out to you of, you have to do your own thing and make your own decision and do what's right for your system. So it says header stuff like activate the probe, do your T equal probe M6, call G700, 710 French metric, G94, whatever you need, do it. In general, most people like to use Oriaxes for their rotary axis commands for their approach points. So if you want that, do it. And then go ahead and get your machine clear your part. So it's a standard header that you'd put in any program. Now we get into something interesting. At this point, we're going to turn on Traori. We need to have the tool length active at this point. So if you've already got it active, fine. If you need to call D1, do it here, whatever. Call your work offset. Call G54, 517, whichever one you're using, it doesn't matter. The reason that it doesn't matter is because the next thing I'm going to do on the next line is, this is one of those dumb copy and paste lines where you don't have to do anything. I'm going to save that value into a local variable named work ID, and then I'm just going to use that all over the place, because there's going to be various cases where I'm going to turn the work offset on and off in some of these background functions. I need to know what value is active. I need to be able to read it. I need to be able to write to it when we're done. So instead of asking you to keep putting that in a couple dozen times, I'm just going to save it as a variable and work off of that. So now we get to approach the first ball. Now when we talk about the approach the first ball, if we look in the manual, I'll go ahead and open that up. Again, you'll have this as a PDF. Your job as the programmer is to drive to the first ball. You can have any orientation you want, as long as you're pointing at the nominal center of the ball and you're keeping your ball one approach distance away. Please scroll down. You see a picture of my ball. So we define this approach distance in the header. So what you guys have done in your program is you've driven the probe to some point relative to the center of the ball, or at least where the center of the ball should be. Obviously it's going to be off a little bit, because that's why we're probing it, is to go find it. But you drive to that point in space and you stay one approach distance away. Again, because you've entered this approach distance in the header of the program, I know what it is now. I can read that in the program. I know what the ball diameter is. So what I can do is I can take the orientation of the machine in space, I can take that approach distance, I can take that ball diameter, and I can calculate where the center of the ball is supposed to be just from that information. The reason that I do this is that this eliminates the need for you guys to figure out how to put in your post a array of where the center of the balls are supposed to be. You just drive to a point where you're pointing at it, you stay a distance away from the ball surface, and I'll take care of the rest. So this can be any orientation you want, it doesn't matter. Now, when we get to here, it says approach the first ball staying 1 approach distance away. Great. Here's the next line, and this is a very important line. You're going to need to switch to Ori WKS if you're not already in Ori WKS, and then you're going to need to do some kind of alignment to the ball, or to the orientation on the ball, with a orientation command. I'm going to keep using an example of a C carries A gantry because it's common. CB, tilt rotate table machine, doesn't matter. It's all the same at this point. I need the orientation command here because in the cases of, for example, when you have a machine where the rotary axes are not perfectly aligned to, we'll say, X and Z, in the case of an AC machine, or if you have the case where you're coming in and you're verifying numbers on a work offset where you've already got a couple of rotational components in there, if we don't do this Ori WKS command followed by an orientation command, then my calculations are going to be off. I'm going to think that the ball is in the wrong location, and then everything's going to be messed up and nothing will work. So this is absolutely critical. Now, I'm sure that there are plenty of people sitting there thinking, wait, I don't want to use these commands because that has the potential for my head to flip around. In some cases, yes. There's a couple ways to avoid this. One is to, when you're doing your approach moves, you're free to approach however you want. If you watch those videos, I'm bouncing around in space in all kinds of nonsense orientations just to demonstrate that it doesn't matter. Get there however you want to get there. So if you want to do something like, if your nominal position is going to be C0A45, go ahead and drive them to C0A45. And then while you're off in space and way away from your part, you can call this orientation command. If you've picked some good positions that are far away from the pole, it's very low odds that you'll get a head flip and it'll go around. But let's say that you would get a head flip here. If you're off in space, it doesn't matter because the way I do my calculations, I don't start calculating center of the ball till this line, till this next line. So if you need to do more approach moves in X, Y, Z without changing the rotaries, as long as you've lined up here with Ori WKS and an orientation command, as long as you've done that, you can do all the X, Y, Z moves down here that you feel like. So if you want to retract, do it all off in space cleanly, and then come in closer, go for it. Whatever works for you, because you have these choices, you know your machine, do what makes sense. So, we'll throw that out. And then this chunk is going to get real repetitive because we're going to do the same thing for 3 balls in a row. We're going to call the first cycle I wrote, which is creatively GSK 3 ball before probing, because it's the GSK 3 ball probing package. And this is a command that we call for me to be able to calculate things like the center of the ball. Now, if you look at these variables that we're passing in, one of the nice things here is that this whole line can be a dumb, blind copy and paste in your post because there's nothing you have to touch. I'm reading and writing out of some of these arrays. I'm reading numbers like ball diameter and approach distance. Again, if you're post, it's easier for you to hard code those numbers, do it. But the rest of this is all give me copy and paste. I don't even make you count ball numbers. I do that internally, and you don't even have to touch it. So we call that. I get the ball centers prepared, and then we probe. So I put this in braces because you may want to use the HMI advanced cycles, or you may want to use a different variant of 997 than I picked. Whatever works for you, doesn't matter. Use the right thing. So I've got sample 997 call. If you use the variants that have the probe rotating so you keep touching the same side of the ruby every time, that's better because that will be more accurate. And honestly, the whole point of using these cycles is that we can have different head orientations for each ball. If it's practical to limit how much you move the head, in general, that does increase the accuracy because now you're introducing less error to the measuring results from head motion. But if you can't get there, you can't get there, and that's why we're doing this. But if you can limit it, do it. If you can keep it in a range of 20 degrees or something, do it. If you can't, then you can't. But the less you move the head around, the more accurate it will be. All right, so we finished probing. Now we run a cycle GSK 3-ball after probing. This, again, is one of the ones that I've given you in that set that you downloaded. The OVR variables, these are results from the probing cycle. These are common for HMI Advanced or for operate cycles, so it'll work for either. Then the rest of this is dumb blind copy and paste. Actual is one of the arrays, the ball number, the work ID, and then this measured diameter is an output. So we get a curly brace line. Now you get to retract the machine however you need to retract the machine and move to the next ball. So you've seen in my videos that I do some very bizarre motions between balls. This is where it goes. And I said this is going to get repetitive because we're back to ORIWKS. We're going to line to the next ball with an orientation command. We'll call the before probing cycle. We're going to probe, call the after probing cycle, retract. So now we've just finished probing 2 of the balls. And unsurprisingly, we're going to do exactly the same thing the third time. Retract, move however you want to the next one, change the orientation, do whatever you feel like. ORIWKS, line up with another orientation command, call the before probing function, probe it, call after probing. And one of the things that I like to do as a personal style is that before I calculate all my results, I like to get the machine clear. That way, if there is some kind of weird error, or we'd say, okay, well, we measured these balls and we found out that they're out of tolerance, so we can't run, we're going to stop the program. We've already got the machine clear and the operator doesn't have to get himself clear. So retract the machine, get it clear, and then we go into a final cycle called GSK 3-ball calc frame. Again, this is a line that's just a complete dumb blind copy and paste because these are all some of the variables I defined in the header, and by putting those variables in the header, you don't have to do any real work in the post here. You're blindly dumping a line. I'm sorry, there's a fuzz of a white lie in here. The fuzz of the white lie is this last variable, which is true or false. And the purpose of this last variable is that it gives you the option of, are we going to update the work offsets or are we going to leave them alone? The reason that I put this in is that, especially for people who have very high value parts, they'll commonly do all of their probing once, activate all the fancy new work offsets that they've calculated, and then once that's complete, they will reprobe everything just to make sure that things turned out where they were supposed to be. Because if, for example, there was some kind of error in the probing and we picked up a bad value because whatever reason that happened out in the physical world, to them, spending 5 minutes reprobing something is far better than spending a day and a half of machining time on a part that took, 3 days of machining time on other processes to get to this point. The high value part people like to do more verification than people who have are starting with pieces of billet. So this gives the option to run as a update the work offsets or not. And internally, what this is going to do is that cycle 997, the standard one where we do 3-ball, it uses a function called MIA-frame to do the 6 degree of freedom work offset calculation. I'm using the same thing. I'm just feeding all the values into it for you. This calc frame is also where I define all the log files and generate all those and give you all kinds of great things. In the Word doc, it'll also give you a list of what all these different outputs are, because some of the things we're feeding in are like, what are the positions where we found the balls, where they're supposed to be. Then you get some other ones, like this max error is a personal favorite, because what that is that after we've done all the new frame calculations, we know where the balls are. I did the frame calculation. I can calculate, all right, so with the new work offset applied, where are those balls going to be relative to where they should be in that new frame? How far is each one of them off? Very few people care about the actual individual XYZ components or the per ball. They just want to know that all the balls are within some tolerance, like 2 thou or 20 micron or whatever you want. This variable returns a value that you can interrogate, and I'll show you this in the example from the machine of how I did this. You can read that, and you can check and say, okay, is this in tolerance? If yes, run the part. If no, stop and call a supervisor or do whatever you do in your shop. But there's a couple different components I give you here as outputs. There's a lot more information in the log file as well. but this is the ones that you would use to decide to pass-fail the part and run. So that's the line where it is. So we got an M2. So when this is all stripped down, we're talking about a grand total of 35 lines. And a huge chunk of this, I kept saying, and we're going to copy and paste, we're going to copy and paste, we're going to copy and paste. You've got standard probing cycles, and you've got motion. So I've stripped this down as much as I possibly can, and I've really buried everything in the cycles that I've given you. So now what we're going to do next is I'm going to take a look at the next program, which is what I ran on the machine, which it has all the motions in it. GSK 3-ball main is the program that I ran on the machine, so we'll take a look at that. Again, this is going to be real repetitive compared to main minimum, which is the one you use to develop your post, but this is real numbers. I happen to do this in metric because my machine was set up in metric. So got an approach distance of 5 millimeters, about 0.2 of an inch. Ball diameter is, I have a 1/2 inch ball, so it's 12.7 millimeter. In this program, I've also made a point of indenting all the stuff that is the things that must be blindly copied and pasted, just to sort out what's required and what you get to do freely. So again, these variables that I define, you have to dump them in. They have to be in the program, but you don't have to touch them. I comment out my call the probe because reasons. Put in G710 for metric, orient, turn off all kinds of offsets, do a retract move. If you see this line in any of my sample code, go ahead and delete it because it shouldn't be in there, but it makes it easier for me to run repetitive tests. What I'm doing is I'm copying a work offset from one to another so I can always start from a common point. But that shouldn't be in a real program. Hopefully that's not in the program that you guys get download. So turn on the transformation, store my work ID, approach my first ball, and you'll see here that in this case I was using this B carry C table machine. So I move them to some nominal positions, B35, C20, and then I give it a A3, B3, C3 command, which happens to match nominal B35, C20. The more decimals you can use here, the better. I use 8 in these programs. If you can go to 10 or 12, that's even better because then that pushes all the errors out into ranges that are just completely and totally impractical for all machining. Even though 8 decimals in metric is far beyond what we could actually get out of a machine, it does make the math work better and prevents rounding error from creeping up into numbers that you do care about. So I'm changed my orientation. And I did all this while I was out in La La Land. And now I come in and I approach the ball at a good position, staying one approach distance away at this orientation. I call my before probing stuff. I probe. Call after probing. Again, these indented lines I don't have to touch. I retract the machine, move to the next ball. I spin around in circles and dance just to show that it can be done. Come back in, line up on an orientation again, which happens to match my B10C150. Come back in, probe. The way I did my math for my part is that because I don't have a CAM system and I was doing all this by hand, I just did a little bit of math here based on nominal positions. You don't have to do this math. That would actually be a silly thing to do if you have a CAM system. Just put your XYZ numbers in. So call before probing again to prepare all the data that I need for this ball. Probe it. Call after probing to take the data that we've got from this ball and convert it into the formats I need. Retract, go to the next ball. We'll say that that's done. So we've finished 3 balls now. I'm retracting. I'm going up, and away where everything's clear. I call the 3-ball calc frame, which is going to give me my new work coordinate system. And then what I'm going to do is I'm going to evaluate my results because I have a programmed a threshold of 20 micron into my program. And this max error value gets returned from the calc frame, which is the maximum error at any of the 3 balls. And it tells me, did I pass? Can I run the part? Or did it fail? Do I need to call a supervisor? This you can make up as you wish, make your own decisions. So with all that being said, the next thing I'm going to do is I'm going to stop and I'm going to show you a little bit of what you have to load to get this to run. So we're back at the files that I gave you. And again, all this is documented in the Word doc. But this set of functions of 7 cycles, this all needs to be loaded to either the manufacturer or user directory, the manufacturer or user cycles directories, one of the two, load into the NC and reboot. These are all cycles where the parameters get passed in, so it requires the NCK reset. Like with anything else you're doing on your machine, make archives before you start working on this. Almost all of these are completely dumb, blind copy and paste. The exception is the 3-ball WCS to BCS. I've got 2 lines in here. Sorry, I opened a different editor. Got 2 lines in here where I need to reference the A and C positions, and I'm always going to tell them that they're zeros. If you don't have A and C axes, you're going to need to edit this and make it match what your machine is. So like if you had a CB machine, we change that to B, and we're done. Whatever the names of your axes are, if they're B1 and B2, you got to change them here. But that's all you have to do in this file. Not going to save that. And then calc frame. I'm going to give you a log file when all this is done. The thing about calc frame is that I had to hard code a path in here for where am I spinning my log file to. You'll also see that I did something fancy here. And if we are in metric, you always get 4 decimal places on the linear values. If we're in inch, I give you 5. Rotary numbers are always 4. And another edit is that if you're using Powerline or any solution line before software 2.7, it's missing a function called sprint. Sprint is a string formatting function that cuts off the number of decimal places I have. So if you're running this on an older system, set this to true, and I'll use an alternative formatting function instead. It should be equivalent, but I wrote all the originals using sprint, and it was easier just to put a variable in with a choice here. So we get back to the path. What I do here is I come up with an array, going to put a timestamp on the path, and you'll see the path where I'm going to write my log file, which is workpiece directories. I make a new workpiece directory named GSK 3-ball logs, and then the log file is going to be named GSK 3-ball, and then I start shoving pieces of the timestamp in here, and then I end it with .spf. In all reality, this is a CSV formatted file, so once you're done with the files, you copy them off to wherever you're going to use them. You rename them from .spf to .csv, and you open them in Excel, and life's good and easy. If you don't like the names that I'm using, this is where you change them. So come on in, change them, and this is the only thing that you need to touch in here. So we close those out. And now, let's go ahead and take a look at the log file. So here's one that I'll give you this one in the stuff that you download, and I've already converted it to CSV. Due to some technical limitations, instead of showing you the SPF file that I've renamed to .csv because I can't open it on this computer, I made a screenshot. We're going to stare at that instead. So when you open this up as a CSV file, you're probably going to have to resize your column so you can see something useful. But what you'll get is you get XYZ components in columns here. You get the XYZ rotations in the next set of columns. I've done as much as I can to split this up because I'm going to assume that if you are one of the log file people that like more data, that you're going to write some kind of parser that imports this into something else. So instead of making you parse characters, I've tried to split everything up as much as I can for you. I have a full timestamp here, and then I have the individual pieces already broken out for exactly that reason. And I also give you the full path and the top-level program that's being run that generated this log file, which may be valuable to you in some form of data sorting later. I give you the nominal ball diameter, your units, tell you which work offset you're dealing with. In my case, I'm dealing with G517. And I give you the original work offset values So in this case, I already have about a ½ degree rotation in Z because of how I mounted the plate with my 3 balls. When I say how I mounted it, I mean poorly. So then it tells us that our correction values are going to be very, very small, which is kind of expected since I've run this several times in a row. This is more or less a error of magnitude that goes along with repeatability of the testing that I'm doing. What you will also notice is that if you pulled out a calculator, you would see that the updated offset values are not just my original and results added together. It's a frame concatenation. So my original work offset is applied in a twisted frame based on these rotations relative to my resulting frame. So you can't just blindly add them together and call that a meaningful number. You have to do some matrix math to get actual numbers, which I've done for you. You get the original, you get the updated. Life is good. Carry on. Then I give you a bunch of data for what I did for each ball. For example, I give you the measured diameter of each ball. I tell you where it is in the BCS and the WCS. The BCS, if you're not familiar with that, is the basic coordinate system. And what that is that's the frame that we use that is defined after Traore is turned on. So for machines, gantry machines where you have 2 rotaries on the head, generally speaking, that means the table on the floor or the concrete. For machines with tilt-rotate table, like I have in my videos, the BCS is generally going to be have the 000 at the origin of the table. And if we pulled out a marker and drew on the table and we drew X, Y, Z, as that table spins around, the BCS is spinning around with it. So one of the things that I do to help clean up and simplify some of my math is that I always take all of my points that I found, convert everything back to my BCS, do all my alignments down there, and then I'm working in a common coordinate system. It makes the math a bit easier for me. The WCS, there are many WCSs that I'm using because I'm moving it all over the place during the calculations. What I mean by WCS here is that this is in the work offset that we're programming. So in my case, G517. So the target position is where is it supposed to be. And then the actual position, what I've done is I took the BCS actual, where did I find it in the BCS, and then converted that with the new updated offsets of where would that point be in that new frame. So this is a calculated value. Then I give you the XYZ component of error for each ball. And then I do square root of the sum of the squares to tell you how far off is that ball center as a true linear distance. Because most people really don't care that it was off by 37 micron in X and 15 in Y. They care that the grand total was 40 because that's what they're going to use to say run the part or not. When you saw me talking about that max error value before, it's based on this error value. It's whichever is the largest for the 3 of them. They're always unsigned, so they're always positive. And so we can look at the data and we can see what each ball did. Now, if you're going to pull out your calculator and start checking things on me, you're going to say, hey, some of these error values are kind of big. You said you corrected this. This is a corrected frame. Ball 2, for example, is out 51 micron, which is about 2 thou. Shouldn't that be better with a corrected frame? And I would say, yes, it should be. If I had a plate that was holding balls that had been accurately machined and accurately measured, and I had a machine that was calibrated that I was using to do the measurement. The reality is that I made this plate on a different machine that is not calibrated, hasn't had pitch error comp done on it, brought it over to the machine that I did the videos on, which also does not have pitch error comp done on it, also does not have a decent Traore calibration done on it. So I know that I'm introducing error from somewhere. And if you look at my target positions, these are nice round numbers like 250 and 125 and 225. Those are what I programmed in. I never actually measured this on a meaningful system. So yeah, there are going to be errors that you can't get rid of by correcting the frame more because they just can't be, we can't move a single frame to correct them because the balls aren't in the spot that they're supposed to be relative to each other. The last thing that I'd like to show you is that if for some reason you have to get into any of these cycles and do any editing or debugging, you're going to notice that all the variable names are grossly long. The reason that they are all grossly long is that there are some machine data that can be set which allow any variables within a subprogram to become global scope. You may have noticed that I've completely and totally avoided the use of GUDs anywhere in this. There's no def file that I give you, and I don't tell you to make any of them. Just pass variables back and forth, which is good. But let's say, for example, that you had one of these machines that's delivered where all variables within all programs are global scope. They basically act like GUDs. They're passed back and forth. Because a lot of these names I'm reusing them over and over and over in each program, like I'm passing my ball diameter in and out of programs constantly, and it'll go into different sublevels. If I created that in a lower level and it already existed, it'd bomb out on me telling me I can't use ball diameter, it already exists. So the reason that all these variable names are really long is that I've prefixed them with the program name. So like this is GSK 3-ball calc frame. Okay, this time I didn't completely prefix it. I had to drop it to get length short, but they've all got a common prefix. So if I want to make my program more legible as I'm trying to debug, I'll do a find replace where I'll take this GSK 3-ball calc, and obviously I'm working on a copy of this. Don't work on your original one, and I'm just going to replace it with nothing. And I did a replace all. The variable names have now gotten much, much shorter. Same thing happened with the local variables. These guys were all prefixed the same. And the program just became a heck of a lot more readable. So if for some reason you have to debug something, this is a way to do it. This is the last thing I wanted to show you, and I hope this is helpful and useful to you, and I hope it helps make your parts turn out better. Good luck.
Siemens. Ingenuity for life.